So good morning. I have the pleasure to introduce Jochen Wilhelmi. Jochen is a longtime member of the demo scene and is the author of Inca 3D, which is a Maya to WebGL exporter. And that's what he will be presenting today.
Hello. My name is Jochen Wilhelmi, and I today talk about exporting 3D scenes from Maya to WebGL using Clang and LLVM, which is an open source compiler framework. What I'm going to talk about is at first what is WebGL, a short introduction to WebGL for those who don't know it yet, and some principles of illumination, so how to render scenes that are looking good. And then the Inca 3D Maya to WebGL exporter. There I give some examples and a bit of technical how it works. And in the end we will see a WebGL demo. So what is WebGL? It's OpenGL for the web browser. It's quite new, was finished in March of 2011. And you can program it in using JavaScript. And it's legacy free and restricted to the necessary. It means it has no fixed function pipeline anymore, like the old OpenGL. And it can render using DirectX on Windows using Angle, which is a project by Google, and means almost native graphics layer engine, which translates DirectX calls and shaders to OpenGL and GLSL. So for those who are not so firm with computer graphics, some principles of illumination. And, this is flat shading using the Lambert illumination model. Here you see that there are this sphere is made of some polygons, and because of the flat shading, you clearly see the polygons and also the quite low resolution of the polygon mesh. And now the goal is to improve the lighting, make the sphere look more realistically without adding any new polygons. So the first step is using the Phong shading and still Lambert illumination. And the Phong shading is an interpolation principle that makes look the polygons smooth, even though if they are still flat. The model has still flat surfaces, and that's why you can see this on the outline of the sphere. It's still like still has corners, but the lighting looks more smooth. So the next step is still Phong shading and Phong illumination, which adds a specular highlight, which makes it look more realistic, but still like plastic. And so the next thing is the texture mapping. And the texture mapping is a technique where you wrap an image around the sphere so that it gets some surface structure, but it still looks very clean and artificial because the lighting does not match the bumpiness of the texture. And for this, tangent space normal mapping is introduced, which modifies the lighting per pixel using a normal map. And now it's combining the texture mapping and the tangent space normal mapping. We get this appearance, and this already looks quite realistic. Because there's still more room for improvements, but this is our last example for the introduction of lighting. Now, now I can show you some examples of what to do with Inca 3D Maya to WebGL exporter, and the motivation of it. The motivation is the artists have their favorite tools, for example, Autodesk Max in Maya or Softimage, and I like to support them directly instead of writing an own tool. So many game engines, for example, have an own editor, but here the goal is to use the existing tools directly. And then of course, we want to have every attribute animatable, for example, the position, rotation, scale, or the diffuse and specular color of a shader. And all these attributes have to be changeable over time. Then in the example of Maya, there's an embedded scripting language called Mel, and this, of course, is a useful tool which could be supported. And the vertex deformation for character animation or shading networks and particle systems are all features which are already in the existing tools, and that's why the question, why not supporting them directly? And but this is not an easy task, and this task I try to solve with a compiler-based approach, where these features are translated to code instead of data. And, the history of the project started in about 2005 with the first idea of a compiler-based engine, but compiler technology is quite a complicated topic. That's why the project came to a halt. But in 2008, on a demo scene party, someone recommended me LLVM. And then I restarted it with LLVM in mind, and already on the next demo scene party in 2009, I had a first working version for OpenGL and CGFX from NVIDIA. But I replaced CGFX and then used GLSL instead. Because, for example, on mobile platforms, there's no CGFX support. And 2011, WebGL also was added. And because of this compiler-based principle, it only took a few months to support WebGL starting from the OpenGL code. Now some examples. Also, I'm not an artist, so they only show some technical aspects. For example, I have a bouncing Amiga ball. This is controlled by a Mel expression. And can make some 2D effects by the texture displacement. So one texture controls the displacement of another texture. Actually, the offset of the UV coordinates are controlled by another texture. And we can do projective light sources. This is a spotlight that projects a checkerboard texture into the scene. And also things like brushed metal are possible using an anisotropic shader. Here, the direction of anisotropy is modified using a texture map. So the circular patterns are produced. And also deformation is possible where the vertex, the position of the vertices are modified. And this vertex deformer is compiled into the GLSL shader. And here's a very new feature is a picking feature. So we can use the mouse and determine the object that is under the mouse, and then using this to change an attribute. Also in this case, the incandescence of the shader is set to red, and this works by rendering the object IDs into a frame buffer, and then at the position of the mouse, we read back the pixel, and this holds the object ID. And, so that's why it's quite fast even on JavaScript and WebGL. And the character animation is also possible. So now the question, how does it work? The workflow overview is that it directly goes from Maya into WebGL, and other approaches are reading FBX or Collada, but these are in my workflow only used to transfer between other tools and not to the engine. So supporting 3ds Max would mean writing a new exporter for 3ds Max, because this way more features can be exported. For example, shading networks. FBX and Collada don't support shading networks of Maya. So I can show how it works in the how it actually works. Here we have the bouncing ball. And this is our bouncing ball in Maya. And this is simply a mail expression that this is our expression that modifies translate. Translate y and translate x are a set of the sphere. And so now, for example, we can modify the height of the bouncing, and now it's like this, and we can export it, and now reload it. We have the bouncing ball like this, and for example, we can also change the color. For example, the ball starts in black, and if it's on this side, it has to be, for example, red. And now we see that the color attribute of the shader is animated, and now we can export it again, and now it fades from black to red. And it's also possible to, for example, set a texture map. You can also use Maya to preview it. Now the ball has green grass on it, and we export it again, and now the ball has green grass on it. And, so it's in a classical implementation, you would do it like this. In custom code, you look up the node, the transform node of the ball, then calculate the position and set it again. And in your scene graph, you have the transform node that holds the position, rotation, scale attributes, and calculates the world metrics from it. In this node you have to find, for example, using its name or whatever. And in a compiler-based implementation, and of course in Maya it's also done like this. We have a dependency graph and an expression node that gets the time as an input and calculates the position and outputs the result to the position of the transform node. So this can be seen here in the hypergraph. Here's the time, then this goes to the expression that calculates the position, and here the output of the expression is connected to translate x and translate y of the p-sphere. This dependency graph in general is consisted of nodes, and every node has attributes. You can connect these attributes arbitrarily, and a loop-free dependency graph can be transformed to a sequential code. So the pipeline of the exporter works like this. First, the dependency graph is exported, then this is translated to C++ code, and in the last step this is compiled to JavaScript and GLSL using Clang and LLVM. And the first step I showed you in Maya, this the time connected to the expression, and this connected to the position of the sphere. Now the second step looks like this. You have the expression node that calculates the position, and then the transform node of the p-sphere calculates the matrix from its position notation scale inputs. And the last step is Clang and LLVM. And LLVM is also used to split up the code between JavaScript and GLSL. The scene graph is, of course, executed completely in JavaScript, but the shaders have to be split up between GPU and CPU. And for this, there's a material program, which is, of course, my own invention. So there's no material program on the GPU, but this has to be done on the CPU, and a transform program that calculates the transformation. Or for example, you have three materials in the scene and 100 objects. Then of course you have more transforms than materials, and so that's why it's also the execution count. For example, for a typical scene, you have 1 to 10 materials in the scene, but if you have many objects using the same material, you can have, for example, 10 to 1000 transform nodes, and that's why this distinction is made between material and transform program, and these two programs then transfer their output into the GPU, and the vertex shader, for example, you have 1000 to 100,000 vertices in your scene, and 1 million to 100 million pixels in your scene, which are calculated in the pixel shader. So, for example, if you have overdraw, for example, 10 trees standing behind each other, then you paint each pixel more than once. So the pixel shader can be executed more than once per pixel. That's why you can have, for example, up to 100 million pixels that have to be calculated. And but here also we see that the heavy work is done on the GPU, and only a few calculations are done on the CPU and in JavaScript. So the lower performance of JavaScript does not really matter, because it's important to have everything on the GPU, or the heavy work on the GPU. And are there any questions until now? Because now the last part is showing the demo created with this exporter.
So you're actually handling null script expression nodes?
So the question is if I'm handling MEL expression. Yes, of course, there's not everything supported from MEL, but the basic calculations and if and else and some control flow is supported in MEL.
So, how is the MEL translated? Is part of it sometimes or does it always run all of these activities, always in JavaScript? Like, how does that translation?
The question is, how does the translation of mail work? So it's done only to C++. So my intermediate language is C++, which can be read in by Clang. And that's why there's a translator from mail to C++.
Okay, so the mail script always runs in JavaScript.
Yes, from C++. I think there's no possibility in Maya to use mail in a shady network. That's why the mail is always runs on JavaScript inside the scene update.
What happens when there are loops in the graph? And the second question, what's the largest node that
The first question is, what happens if there are loops in the dependency graph? And this leads to undefined behavior, but it doesn't blow up everything. The only thing is that that one connection uses the value of the last frame, because the loop is broken up, so an arbitrary connection is removed, and also at least for determining the order of the nodes, and that's why this connection uses the value of the last frame. And the other question, the largest mail script, I think it was not very large, but for example 15 lines, but I see no restriction in size. There are of course restrictions in features, but not in size.
Do you go to the Nash export pipeline? How does that get converted to C++ as well?
No, the mesh and index data are handled like data, and of course you can do vertex format conversions can be done with LLVM, but this is basically a data path. So the meshes are exported and handled as data and then written to a data file. Now, the SR Cyprine WebGL demo. So by the way, the SR Cyprine is a immunosuppressive drug, and it was done with a demo group Alcatraz. By the way, on Monday I first visited Alcatraz myself, and made the second place on the demo party Evoke in 2011 in Cologne, Germany, and also won the second place in the Mozilla demo online competition. Now, as everything is JavaScript and WebGL, we can launch it directly from the browser. then thank you for your attention. And you can get a public beta at www.inca3d.com.
So you mentioned actually offline that entire demo was basically exported directly from Maya. Like there's very little handwritten JavaScript code in there.
So basically, the question is how much of it was exported from Maya. Basically, it's the 4 scenes, the 3 parts are scenes in Maya, and the overlay that shows the introduction picture, and there are always some pictures in between. This is an overlay scene. So the JavaScript code only controls which scene is played when. And so it's can also here this is all code. This is a draw scene code which just controls which part is played when, and in the last in the overlay, of course, disables the depth test, and that doesn't interfere with the existing scene, and so this is the whole main part, which is written by hand.
Curious, what cases are you supporting
I mean, mail expressions. Basically, all objects are not supported. There are object types in mail, and for example, you can also evaluate the whole scene at a different time and then get the attributes, but this is not supported. So it's basically all basic operators like plus minus, and the math operators and vector operators like cross product and if and else, and so far not even loops are not supported. A for loop is not supported currently, but if and else is supported, and only the basic stuff, but it's but in most cases it's enough. But of course it's ongoing work. I try to support more and more.
As part of the demo scene, I guess one of the things you try to do is to try to push the hardware or the technology not to the edge of what it can do. What was it about this demo that pushed WebGL to the limits? And I'm kind of curious actually why you didn't throw in some maybe skinning animation or two like the export. So what was it about the
Question is, what was the intention of the demo? Also, of course, at this time, and why is skinning not supported in the demo? Also, it has 2 reasons. At the time when it was released, skinning was not supported yet, because this was an extra step to get the vertex deformers into the vertex shader. And but now now it is supported. But and the second reason is that I didn't have any good content for it, because the demo is mainly made of existing content, existing scenes and existing images, and I just glued them together and made the credits part and the last part, and Kaito of Alcatraz made the music for it especially, but the content was mainly of existing stuff, and it didn't include any character animation. The question is how this decision made between CPU and GPU. It's so everything that is in the scene dependency graph is always executed on the CPU. But for the shaders, the first step is creating a C++ shader, which has which is one block of code and no distinction between vertex and pixel shader. And this is analyzed on the LLVM intermediate instructions. So, for example, if you have a vertex data coming in, for example, a UV coordinate, then every instruction that operates on this UV coordinate, of course, has at least to be in the vertex shader or in the pixel shader, because you can't execute it outside if it depends on the vertex input. So every instruction in the code is classified at which stage it has to be executed, and our stages were these four stages. So every instruction in the shader is classified if it runs in one of these four stages.
So I could imagine that if you hand wrote more code, then you could do tricks with the geometry. Maybe the question is, are you doing any tricks like the scene where you're traveling, where you're traveling along the long track? Do you have actually a piece of geometry this big and you're moving the camera along, or do you have a segment this big and you just keep moving the camera through it over and over again? Like, can you do these kinds of tricks?
There's another sort of four segments of tracks, and I can show it if Maya 2011 has started. And so every piece of track, if it leaves the viewport, then it's switched back to the beginning of the track via a mail script. So every piece of track makes a ramp-like track over time. So it passes the camera and then jumps back, and then passes the camera again and then jumps back. And there are four of these who do this interleaved. So you have the impression of a continuous track. But, so I can show you it in a minute. And of course, the credits that are flying by, the greetings that are flying by, is also only one plane, and which shows a part of a texture map, and this part is then switched. So like on an old omnibus, you have a large foil, which is then winded up to show the destination, and it's basically done like this. Here you see the track parts which are jumping back, and this is controlled via a mail expression, and this has this mail expression to control the greetings that are flying by.
So what are the possibilities that you see for interacting with the scene after export? How do you see that working? Does it work now?
The interaction works by accessing the attributes. So for example, if you have some attributes, so the translate y. If you change it, then Maya tells you how the attribute is called. In this case, is greetings.translate y, and in JavaScript you can look up this attribute by this string, and because in JavaScript every attribute, all attributes are put in a large array of float 32, and so the exported code has a table of all attribute names and the offset in the array. So you can just look up the array position and then write something in, and if you then recalculate the scene, then the attribute is changed. This is, this is, for example, done here. So I get the attribute within JavaScript, the scene.get float vector. But this, of course, JavaScript is not typed, but this is only for a bit of checking. So if the artist changes the scene and it's not a float vector of the given amount, also of 3 anymore, then you can get a warning that the scene doesn't match your code anymore. That's why here's a bit of type information, and then you use the my attribute name, for example, joint1.rotate or file1.colorgain, and then these are references to the JavaScript arrays, and then you just need to fill them with new values. And if you then update the scene, these values are calculated into the scene graph and then used for rendering.
There's a nice looking JavaScript APIs. Those are things you wrote on top of
I guess this is used to access the exported scenes.
Okay, so you wrote that on top.
Yeah.
Maybe I just missed the first part. I guess I'm still a bit confused as to like what part of the export pipeline is data, like mesh and scheme information and whatnot, and what part is actually going to be still kind of.
The question is which part is data and which part goes through LLVM. So we can so everything that goes into a static vertex buffer is data. So there are only static vertex buffers. There's no dynamic vertex buffers. So so everything that goes into the vertex and index buffers is data. And everything else, for example, also calculating the Bowen matrices and this is all goes through LLVM.
So do you handle Maya shading networks, or do you require that you write the shaders in Maya and then you do the translation step? Like you interpret the fixed function of built-in shading networks and generate GLSL from those?
I guess if you create your own shading network, for example, this is a shading network in Maya. This is completely translated to GLSL automatically. But technically, it's no difference between what is done on scene level. So it's on scene level you have nodes and attributes, and in the shading networks you have nodes and attributes, and that's why it's the same code that does it. And you only have to, you need a different code generator. One is for GLSL and one is for JavaScript. But as JavaScript it also looks like C, but doesn't has types. It only, as every time, uses var instead of float or int. So it's also not a big difference.
Do you have a uniform representation of the entire logic of the scene, or is there a specialized intermediate representation for the shading network, and a specialized one for the mel scripts, and a specialized one for the translation of the data. And because earlier you mentioned that you dynamically figure out, by analyzing the intermediate representation, what parts should run on the GPU and what parts should run on the CPU. So, do you have like multiple chunks of code, and you know that there's a hard boundary between CPU and GPU for some of them, and then infer what should be pulled onto the CPU or pulled onto the GPU based on that?
No, of course the exporter knows what is the scene, and it knows what is the shader, and there's a hard boundary. So there is a distinction between scene and shader, and also deformer. Deformer is also handled separately, and only in the last step the deformer and the shader are merged together if you want to execute them on the GPU, because for ordinary C++ and OpenGL you can also do the vertex deformation on the CPU if you like, and so there are some blocks of code which are handled differently, but the language is the same. So there's also for one scene there's one code for the scene itself, and for every shader in the scene there's also one piece of code, and for every deformer in the scene there's also one piece of code.
Where do you see the project going?
Also it could be a useful tool for the upcoming WebGL and web-based applications, for example, advertisements or web-based visualization tools for specialized problems, and maybe even games. Currently, it's only a rendering engine and not a game engine, but if you want to do your game logic yourself, you can do it for games. You can use it for games, and Flash? The question is if it could be used to target ActionScript and Stage 3D. As I think, yes, it would be possible, but so I, for myself, I don't have the time, but WebGL is the future anyway. Yeah. So are there any questions?